every pixel for some objective function. And so in this case, this is just referring to a review article if you're interested in this. But we asked this question with our collaborators, and this is the type of device that they came up with. And we can have drinks and talk about why it looks like it does, or we can make it and see how it performs. And indeed, we could isolate single NV centers that were coupled to these devices, and then we could see about a 14-fold extraction in the efficiency of that zero phonon line relative to theory. Okay. But so the NV centers that were in this device weren't the best, but they were actually pretty good. So this is what they looked like after they were implanted. This is, to us, it was pretty hopeful that we would be able to stabilize at this level. After we fabricated these devices, there was no signal at all from the NV centers anymore. And that was because simply the exposure to the plasma that needed to be used to etch the gallium phosphide, which did not etch into the diamond, left the nitrogen vacancy center in the wrong charge state. We were able to bring it back somewhat, but you'll notice that I'm cheating here. The frequency is weaker, but then also the frequency range is different. So this is telling us we can't even expose the surface to a plasma without affecting it. And so where we are right now is we believe that for something like the NV center in particular, which is the most successful defect so far, you need to avoid all diamond fabrication. You want to, and people are still working on this, actively control the surface, get the defect how you want it to be, and then simply assemble your cavity structure onto the diamond surface. We have moved on to work with this assembly type structure. We're now completely fabricating on gallium phosphide and oxide. We are stamping them onto diamond. We've gotten some very promising results with the silicon vacancy that you can look in this archive paper of getting cooperativities that are starting to be useful now. And then of course, we'll want to transfer this to the more sensitive nitrogen vacancy center in the future. Okay, so taking a step back, we see that quantum defects behave almost like atoms. It's kind of a catch-22 in that because they're in a system where you can actually have more control over them, like put electrodes, tune them, they're also pretty sensitive to their environment. So it's the same features that lend themselves to scalability also present challenges. Hybrid photonic platforms appear promising to minimize disturbance of these qubits, but this is just one strategy that people are tackling. And I kind of want to overview the field of what people are doing. One, of course, is materials innovation, right? We've done implantation studies, like how do we heal the lattice? How do we gently create nitrogen vacancy centers? Are there other lattices that we should be using, other defects that we should be using? The other one is tuning. So we've done work, and in fact, in the demonstrations of entanglement with NV centers and SIV centers, always you have to tune one onto resonance with another. And so these are integrated electrodes, and you also tune them as a function of time because they always drift. You just need the drift to be slow enough that you can do this type of control, right? Emission enhancement, I've already talked about. Protocol development, how do you have a protocol that's more robust to imperfections, like a protocol that's more robust to inhomogeneities, for example. One of my favorite ones is frequency conversion, which is, so someone mentioned or asked a question and said, well, so all we have to do is get rid of the inhomogeneity. That's true. But you don't actually have to make the defects identical. If you do frequency conversion of the two photons and convert them both to the same system frequency, you can do the interference at that converted frequency. And that will work. And so frequency conversion is a spectacular tool if it can be made to work efficiently and scalably for these systems, because it does two things: puts you at a frequency you want to work with, for example, telecom, as well as has the ability to erase which defect actually emitted the photon. It can be a very powerful tool, again, if people can get this to work efficiently enough. And then the last one, of course, is new defects. And this is a giant parameter space that I think is extremely exciting, that people in the field are trying to wrap their head around on how to efficiently explore this space. Because we know in this space of there's certain functionality that we want. I talked about one particular example of creating this edge state for a quantum network, which is going to correspond to particular defect properties, which are inherently linked to the materials properties that host a defect. And we know in this space of materials and defects, there's something better than the NV center. And of course, the question is, how do we find it? So I think that's a good place to pause to see if there's any more questions before I go on to the last bit of the talk. Okay, so moving on to semiconductor donor qubits.
Sorry, we're muted. We actually did have one question.
Great.
So what's the implantation energy of the nitrogen ions, and what's a typical annealing temperature?
Yeah, so it depends on what we are trying to achieve. For getting defects that are 10 nanometers from the surface, a typical ion implantation energy is about 10 keV. For the work that we did with those inverse design photonics, I think the implantation energy was like 85 keV. We were closer to 100 nanometers from the surface in that case. We've actually done a study where we actually angle implant at something ridiculous like an 85 or 86 degree angle in order to have high energy ions come in but still be close to the surface. And we wanted to kind of figure out why the 15 keV NV centers weren't good. Was it that low energy damage is a problem, or is it the surface that's a problem? So we did that experiment as well, and that pretty conclusively said in that case the surface was the dominating effect of the coherence and not the implantation energy. We anneal, we can anneal up to 1200. We typically only anneal up to 1100 degrees Celsius.
Okay. And do you tend to get any straggle in the implantation?
So we implant at 7 degrees, which is supposed to help minimize the straggle for ion channeling, but we actually don't have a way, we don't detect whether we get straggle or not. So in our studies, we typically look at a large number. If we just see a few that are amazing, that could be a straggle ion. So we're looking typically for high numbers so we can avoid that. And of course, the big straggle ones won't couple to our optical devices for integration.
Okay, thank you.
Welcome. Okay, so you can broadly separate defects into two categories. One is very deep, super spatially well localized. By deep, I mean deep within the energy band of the crystal, the semiconductor, very well localized defects, such as the nitrogen vacancy center and diamond that you see over here. And then you can also have very shallow potentials for carriers. And over here on the right, you see the wave function reconstruction from a scanning tunneling microscopy measurement of a single phosphorus in silicon. And here you're looking at the density of the electron, psi squared, and you can see that it extends over many, 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 many lattice sites in this case. So this is an extended shallow donor. And people in both camps like to say why their defects are great. I would say that the numbers kind of indicate you can get good defects in either case. The T2 record for a deep level system is in the rare earths at 6 hours for a hyperfine transition at 2 Kelvin. The T2 record for phosphorus silicon is 39 minutes Again, this is for the nuclear spin memory. This was a curious experiment where they actually initialized the nuclear spin. This was an ensemble experiment. They initialized an ensemble of nuclear spins. At low temperature, they increased their cryostat up to room temperature. Then they cooled it back down, and then they read out the state to show that they could get 39-minute coherence time at 300 Kelvin, actually at room temperature. So both systems can be highly coherent if you have, the right host defect combination. The second half of my talk, or I would say the last 5 minutes of my talk, is going to focus on these extended defects, which are studied much less than the deeper defects for quantum network applications. Silicon doesn't have an efficient optical interface. And so we look at shallow donors and direct bandgap semiconductors, such as zinc oxide, where aluminum, gallium, or indium can substitute for the zinc, providing that extra electron, which at low temperature is bound coulombically to the donor impurity and creates a giant hydrogen atom in your system. Some advantage of effective mass donor defects are the properties are derived from effective mass theory, which is a very well-established theory from band structure, or from Bloch's theorem, essentially. And then you have a single substitutional defect in this case, which gives you the potential for deterministic fabrication. Phosphorus and silicon, they get 99.85% incorporation probability for putting in one phosphorus ion. So that's pretty incredible in terms of yield. For a nitrogen vacancy center, you're jumping up and down if 10% of the nitrogens that you put in can yield an NV center. And that is a good center in terms of yield for input. And then long-term, something I'm really excited about but have not been doing work on is that you have an extended wave function, which means you have the potential for combined electronic and optical function. All of the silicon work that's done is, of course, in the electrical domain. All the work that I'm going to show you is in optical control. Okay, so the optical accessibility is not through just exciting an internal orbital of the defect, but actually comes from exciting an electron hole pair across the band gap of the material itself and creating something called the donor-bound exciton, which is 2 electrons and a hole. These are still very sharp transitions. These exist below, this transition exists below the band gap of the semiconductor. It's bound, and you can have very well-defined selection rules that are given, of course, by the symmetry of your crystal. And this just shows an overview that, of course, these will exist in any semiconductor. Gallium phosphide, indium phosphide, cadmium telluride, and zinc oxide are shown here. They all have different, Bohr radiuses that are given by the material properties. They also have different G factors, which can be a proxy for spin-orbit coupling and how good the coherence might be. And what you also can see a little less clear because it's in color plots, but you're getting very well-defined transitions of the donor-bound exciton, which enables you to have optical spin control in this case. Okay. We choose zinc oxide because it has the potential long-term to be a spin-free lattice. You can get rid of all the nuclear spin noise. It has small spin orbit coupling, which means relaxation times, longitudinal relaxation times of the spin should be very long. It has a large exciton binding energy, 50 to 60 millielectron volts, which is a consequence of a large band gap, which can be awkward to work with. We are working in the near ultraviolet. Okay. This is what a spectra looks like on a log plot where you can see aluminum. This is actually an excited aluminum state here, gallium, excited gallium state, and that indium transition you can just make out in this particular bulk sample right here. What has made our lives a little bit easier, here you actually see the ytterbium ion transition for ytterbium quantum computers, ytterbium trapped ion quantum computers. We actually have a proposal to get these types of ions to talk to indium. But it's also helped us because in terms of the optics that exist at this wavelength, given that the trapped ion community has really paved the way for near UV lasers in this case. And so our first test was we had done a study of gallium, indium, and cadmium telluride and really worked hard to understand what causes spin relaxation in this material. And it pointed the way to looking at zinc oxide, which involved doubling all our lasers. And I'm happy to say that that's where undergraduate researchers come in handy. If anyone's an undergraduate in the audience, undergraduates are willing to be bold and go where no one has gone before. I had a wonderful undergraduate researcher who says, I'll try that. And, you know, the first results that came out was about 1,000-fold increase in the spin lifetime because we had moved to this different host matrix. Okay, we have about, 5 to 8 minutes left. I'm going to move on to just two results in this indium donor case that I'd like to share with you. And of course, I'm happy to answer questions. The first result that's happened in the past year is that we can form these by ion implantation and annealing now. So here is this natural zinc, not natural, it's synthetically grown, but it's a zinc oxide substrate where we can see the gallium and the aluminum and the indium. We chose indium to have minimal interference with the gallium and aluminum in the substrate. There's only a tiny bit of indium in our substrate. And we had no idea what levels to implant. So we implanted up to visibly damaging the material to not being able to see it above of the substrate emission. But what you can clearly observe is where the indium line was before. Here's multiplied by 200-fold. Now we have a very strong indium emission peak by implantation and annealing the indium. This is kind of what it looks like as a function of implantation dose. You do get lines that are as sharp as native indium when you're at the lowest doses here. And very promising. You actually don't know if you have things similar to native indium until you do these photoluminescence excitation, high resolution scans, but you can see at least at the 10 to the 9 and below, you have line widths that are comparable or the same as the native indium in the sample. And that's something that's pretty surprising and is not normally observed in systems. Okay. Longitudinal spin lifetime also looks great. The T1 times, these are not coherence times. These are their classical bit flip times, but they are approaching seconds in this case. They're just not a factor for the performance of these systems. Then the second thing that I do want to share is that we do have a problem that we have a bit too much indium, even though it's not very weak. It's not very strong compared to aluminum, gallium in our substrates. So in parallel, what we also did was we actually carved out a sample, a very thin sample out of our bulk zinc oxide, where the layers go from about 500 nanometers thick up to a few microns thick, with the hope that we would be able to isolate single indiums. This is something that would not work in diamond. It turns out if you use focused ion beam in diamond, it causes too much damage and you won't actually be able to observe the NV photoluminescence. But we thought we'd try it. Zinc oxide's a different material. And if we move forward, sure enough, this is the sample. This is the sample in our cryostat in photoluminescence, where we're collecting all the photoluminescence. And then if you filter on where the indium donor bound exciton line is, we can now observe the emission from single donors in this case. And within the resolution of our spectrometer, which is still too broad, you really have to do photoluminescence excitation experiments, but at least within the resolution of our spectrometer, we have resolution limited lines. Okay, so in summary, I've told you that defects are promising atoms for quantum networks. I kind of tend to talk about the problems, which may be a little different from some speakers, but it's because I'm so excited about the system and I'm hoping there's more people that can help me work on the problems if they know what the outstanding challenges are. Each defect is different in space and time, and we have to engineer ways to mitigate the effects of these differences. And then finally, in the large defect parameter space, donors and direct bandgap materials are a promising emerging platform. So I'd like to acknowledge the folks that actually did this work. as well as our funding agencies, and leave you with a beautiful picture, a virtual picture of where I am right now in Seattle, and also state that if you're interested in any of these problems, we'd love you to come and work with us. Thank you.
Yeah,
Thank you. Very good.
Thank you. Great. We have time for some questions.
Hi, can you hear me?
Yes.
Very nice talk. And I was wondering about the gallium phosphide and dioxide. They might be piezoelectric materials. In the case of gallium phosphide, people doing optomechanics, usually for quantum applications. So I wonder, here at the Institute, we do some optomechanics, me and somebody else. I wonder if you see some possibility of using optomechanics for controlling those defects in gallium phosphide, you already know, but in dioxide, what do you think about? Do you believe in that approach?
So we do have a collaboration in gallium phosphide with Mo Lee, who's here at the University of Washington. And that's actually having an integrated system where we use the gallium phosphide actually for frequency shifting to erase information about which defect emitted the photon, like really small frequency shifting. So that's one area we've looked at gallium phosphide. In zinc oxide, we've just started thinking about it. We haven't looked at how you would utilize the piezo, the piezoelectric effect yet.
It was dioxide.
There was a question in the chat there, you can check that.
Nice talk.
Okay, I'm having a little trouble hearing, so I'm not sure if there was a question.
We have it. No, there wasn't a question on the chat. We're just some comments. Other questions either online, unmute, or in the room?
Because I will ask one.
So we have a couple in the room. How about Nicholas go first, and then you can go.
Yeah, I was wondering if you could talk a little more about the origins of the spectral wandering of the NV0 photon line and what exactly you attributed that to.
Yeah, so very vaguely we attribute it to charging and discharging of nearby defects. When it's in bulk diamond, it's usually attributed to other nitrogen because we know that we have nitrogen nearby, and that's actually where you're getting that excess charge, and then nitrogen can exist in a neutral or ionized type state. When you're looking at being near a surface, it's usually attributed to surface states. I know that's not particularly comforting, but the diamond surface is known to be quite messy, and there's known to be lots of dangling bonds. And then for implantation damage, that one is harder to know. So I have not seen anything conclusive in the literature of which defects are charging and discharging that dominate this effect. More qualitatively, you look at this effect as a function of like implantation conditions. Does that, I know it's not very satisfying, but.
Oh, thank you. No, that helps. Thank you.
Okay, we have another question.
My question is a very general question that given all the problems you mentioned here today, how close we are to realizing these quantum networks? You hear a lot that they're coming. Are we close in the next 5 years? We can see one? Where are we?
So right now, the state of the art is 3 nodes separated by a fair distance. That is using nitrogen vacancy centers that are far away from the surface with solid immersion lenses with bulk frequency conversion to get to 1.5 microns. So, you take your photon and you put it through a piplin.
And do they implement the quantum error correction also in those nodes?
No, they do
Oh,
not implement quantum error correction. So that's the current state of the art. In terms of, what's going to happen in 5 years, I think the answer really depends on where we decide to put resources. We can push the nitrogen vacancy center and get that to go further and further and further. I think a lot of people aren't as interested in doing that because a lot of people think it's going to roadblock because you can't get into an integrated device right now. And so there are a couple groups that are pushing the nitrogen vacancy center. It's going to continue to add on nodes. I think we're going to learn a lot from that work. In the meantime, I do think there has to be some significant breakthrough in another platform for integrated devices to really scale.
Yeah, thank you.
So maybe one last question we have from online. I'm not sure if you can see it, but the question was, there are great challenges here in the materials. What are the optics challenges and ultimate applications?
Yeah, Nick, I'm here, so I can ask that.
Oh, sorry. Yeah, go ahead.
Oh, yeah, hey, sir. So thank you for a really interesting talk. And I think that you touched on this a little bit, talking about the metamaterial stuff, but can you maybe elaborate a little bit? What do you think really are the optics challenges? Are they interconnects? Are they architectures? Really, what are the optical challenges here? And what do you think needs to be done in that? Thank you.
Okay, so the first optical challenge, which I think people may argue is boring, but has existed forever, is how do you capture a photon? Right? How do you get a photon? We have our designs and we say, all right, we have this device and now we're going to get 100% collection efficiency, but it doesn't really happen in practice. Especially with, people engineer ideas like near field plasmonics and things that just will not be compatible with defect integration. But it's interesting physics in its own right, which is I think why people want to study, which is interesting to study. The second one, like I said before, is I think being able to convert optical fields post emission would be hugely valuable, right? If you could do this, and people think about transduction all the time. People are saying, well, we want a superconducting qubit to talk to a trapped ion, right? You hear this. Trapped ion is going to be the memory, the superconducting qubit is going to be the processor. And so you have really smart people working on doing microwave to optical conversion, right? How do we do that conversion? It's very low efficiencies. One thing that I don't see people thinking about enough is the bandwidth engineering in really hard to engineer bandwidth areas. And so an example of this is I work with an NV center. It has a photon that's like a 10 nanosecond long photon or a 1 nanosecond long photon. I see people doing all sorts of amazing things with picosecond and femtosecond photons with dispersion engineering and pole shaping, right? I see it and I'm like, can I have some of that? Because if I can do that sculpting with my centers, there's actually more protocols that I can do, but I don't see answers in the 1 nanosecond or 10 nanosecond bandwidth regime of pulse shape engineering.
Yeah, so what do you think about architectures? Is optics going to be involved in helping to make a system architecture that makes it better to do this kind of app, and what's the ultimate application for it is what I was asking you.
Yeah, so I think the ultimate application of optics is in networking. In almost everyone that talks about scaling, even the superconducting qubits eventually say we have to get, optics are the only thing that work at room temperature. Right? And the only thing that work at long distances. So even if we have superconducting processors, we need signals that come in and out optically to connect to other processors. You're not going to build everything that you need into one dilution refrigerator. Similarly with the trapped ions, you can't put them all inside. You can't put enough ions inside the same trap. You're going to need to have optical interconnects. And I don't see anyone who's talking about long-term scaling. It's the same for classical, right? You have a data center. In the end, you need these optical links. And if those don't happen, then you won't have scaling.
So you think the optics is going to be more important in the interconnects rather than the architecture. I agree with you.
But you could also invite someone from PsiQuantum to come talk, right?
Okay,
And
thank
then
you very
can
much.
hear-
Thank you.
can hear that.
Thank you. Yeah.
Okay, well, I think that takes us to the end. Thank you, Jaime. Let's one more time.
Thank you.
Very nice talk.